Welcome to this exploration of plate tectonics, where we decode how Earth's outer shell works and why it matters. In the next slides, we will walk through the mechanical foundations, different boundary types, driving forces, seismic and volcanic consequences, and how modern tools reveal the planet's deep dynamics, all tied together with clear examples and real-world implications. In this illustration, we compare the rigid lithosphere with the softer asthenosphere beneath it, showing how the brittle outer shell rides on a ductile, convecting substrate. That mechanical decoupling allows tectonic plates to move, with mantle convection, slab pull, and stress transmission, serving as the main drivers of plate motion and surface deformation. When plates pull apart at divergent boundaries, magma rises to form new oceanic crust and drives seafloor spreading, producing basaltic pillow lavas and hydrothermal vents. The diagram also highlights symmetric magnetic stripes on the seafloor, which record reversals and provide a clear fingerprint of continuous crustal creation along mid-ocean ridges. This slide contrasts two types of convergence: oceanic plates subducting beneath continents, creating trenches, volcanic arcs, and deep earthquakes, and continent-continent collisions that thicken crust to build high mountain belts like the Himalaya. Both pathways recycle crust into the mantle, generate magma in subduction zones, and produce many of the planet's most destructive seismic and volcanic hazards. Transform boundaries occur where plates slide past one another, producing strike-slip faults like the San Andreas. These faults concentrate shear stress and release it in sudden earthquakes, carving linear valleys and offset drainages, and presenting complex seismic patterns and urban engineering challenges that demand careful preparedness and planning. Plate motion is powered by a combination of slab pull, ridge push, and mantle dynamics, with convection cells in the mantle transmitting forces upward. Global measurements such as GPS and seismic energy release let us quantify these slow but measurable motions and reveal how gravitational forces and mantle drag produce torques that shape plate trajectories over time. The mantle convection engine runs on internal heat from radioactive decay and residual accretional heat, driving circulation through density contrasts. Warm material rises at mid-ocean ridges, while cold slabs sink at subduction zones, transferring thermal energy into mechanical work, coupling to lithospheric plates, and sustaining tectonic circulation across geological timescales. The global earthquake map shows a strong concentration of seismicity along plate boundaries, while depth plots reveal subducting slab geometries and Benioff zones down to hundreds of kilometers. These patterns provide direct evidence of plate interactions, indicating where stress orientations change with depth, and tracing the three-dimensional geometry of Earth's lithospheric dynamics. Volcanic activity reflects tectonic setting. Subduction zone volcanoes form from hydrated mantle melting and produce explosive and acidic magmas. Hotspots like Hawaii puncture plates with stationary mantle plumes, and complex magmatic provinces arise from back arc spreading or slab windows, linking deep mantle processes to surface hazards and exploitable resources. Orogeny describes mountain building through a sequence of processes: subduction and terrain accretion, continent-continent collision, isostatic uplift of thickened crust, and finally erosion and exhumation that expose deep rocks. This cycle not only sculpts topography, but also forms metamorphic belts and sedimentary basins that host important mineral resources recorded in the geological record. Over long time, scales plate tectonics influences climate by rearranging ocean gateways and changing topography, which in turn alters ocean currents and atmospheric circulation. Events like the opening of the Drake Passage or closure of the Panama Isthmus reshaped global circulation, while volcanism and uplift modulate atmospheric CO2, creating feedbacks among the solid Earth, hydrosphere, and atmosphere. Advances in seafloor seismometers, satellite geodesy, and supercomputer mantle models are transforming our understanding of plate behavior, from microplate dynamics to deep slab stagnation and lithosphere. Asthenosphere coupling. These tools improve hazard prediction, guide resource exploration, and extend plate tectonic theory into planetary comparisons, opening new directions for Earth system science and planetary evolution.